In this first lesson of MCT4C, we're going to review some necessary skills in order to be successful in the remainder of this course. So our goals for this lesson are to differentiate between functions and relations, use function notation, and state the domain and range for a given graph. So these are all topics that you would have learned in grade 11, but we're going to review them for the sake of this course. The first thing we need to know is what a relation is. So relations have each input value with at least one output value. So if you plug x into an equation, it'll spit out at least one value for y. So you could have two different values of y, you could have just one value of y, just depends. But in any case, there's a relationship between two variables, x and y, and you can make a graph of that relationship. A function is a specific kind of relation. In a function, each input value, so each x value, has exactly one output value or exactly one y value. So if you plug one value of x into an equation, you will only get one possible value of y as your answer. So if you look at the graph, you can use what's called the vertical line test to see if your relation is in fact a function. So on the left-hand side here, we have a parabola opening down, and if I take a vertical line and move it through the relation, I can see that at each point on the graph, it's only touching the vertical line in exactly one spot. So I would say this is a function. Whereas over here, this other relation is a circle. And as I take this vertical line through the graph, I can see for many of these specific x values, the graph touches the vertical line at two spots. So here, this relation is not a function because there's more than one y value for each x value. So if you have a function, you need a way of representing that function. So in grade 9, you would have had an equation in the form y equals something or other. In grade 11, you would have learned the function notation with f of x. So in this class, when we talk about functions, I might use y equals, I might use f of x, but really y is f of x. So whatever your function is, it's being graphed on the y-axis of your graph. Now, important to remember whenever you're using function notation is what it means. So yes, f of x is whatever you're graphing on the y-axis of your graph, but the labels mean something. Whatever letter you're using, could be f, could be h, could be whatever letter you want here, that simply is the name of the function. So this function is named f. Whatever's in brackets, in this case x, that just represents the value of your independent variable. So you could have a function in respect with time. So the variable in the brackets would be your time variable, or it could be your distance or height, whatever. Just remember, this letter is the name of your function, and whatever's in the brackets is your independent variable, whatever the variable is. Another thing you would have learned about in grade 11 is the idea of domain and range. So domain is the set of all x values in a function, and range is the set of all y values in a function. So another way of saying this is that domain is all of the possible values of x that can exist in your function, and range is all the possible values of y that can exist on your function. And there was a way that we wrote out the domain and range. We used something called set notation. And just as a quick example here, you might remember this notation. Set notation uses the curly brackets or curly braces, depending on who your source is. But what's inside the curly brackets is the set of all the numbers that can exist in your domain. Okay, so the domain is equal to the set of all real numbers. So x is any real number. X is an element of the real numbers such that x is greater than or equal to 0. That's how we would read this. So basically what this means, the domain of the function is any number 0 or higher. So domain is all the x values, range is all the y values, and to write it you use these curly brackets in set notation. We'll do more on that in a little bit. And just for your information, I mentioned real numbers on the previous slide. X was an element of the real numbers, so what are real numbers? Well, it's any of these numbers, really. So you have natural numbers, you're counting numbers, 1, 2, 3, 4. Then we add the idea of 0. So now we talk about numbers as whole numbers. If we add negative values, now we're talking about integers. But there's numbers in between the integers. So between 0 and 1, for example, there's a half or a third or 3/4. Those are numbers that can be expressed as fractions. Those are called rational numbers. Now, there's also numbers that can't be expressed as fractions. So, for example, pi or the square root of 2. Those are infinite decimal numbers. You can't express that as a fraction. So those are called irrational numbers. Now, any of these numbers is part of a set called real numbers. Now, just so you are aware, also, there's something called imaginary numbers, but we don't talk about those in this course. They are beyond what we need to talk about. So real numbers are basically any number you can think of. So when I say x is an element of the real numbers, I'm basically saying x can be any number, fraction, decimal, whole number, negative value, whatever. So here's my first example. I have a line on a grid. Notice the arrows on the line, so that means the line keeps going. It doesn't stop in either direction. So when I think about domain, remember domain is all the possible values of x on this function. My function is this line. Since it keeps going in either direction, well, x can be 0, x can be positive, and the line keeps going in the positive direction, so x can be any positive number. What about negative numbers? Well, the line keeps going off to the left, so x can be any negative number. So really, x is any number that's negative, 0, or positive, and there's no restrictions. X can be any value. So the way I write that is domain equals x is an element of the real numbers. That's it. No restrictions. Now range. Range is the possible y values. Well, same thing. The line keeps going higher and higher, so y can be any positive value, and the line keeps getting lower and lower on the grid, so y can be any negative number as well, and also 0, because it exists on the x-axis as well. So y can be 0, y can be positive, y can be negative. That means y is an element of the real numbers. No restrictions. Now what about this graph? Let's try the domain and range for this one. This function, notice it starts here. This is a point. There's no arrow right here. So the function starts at this point and then it goes upwards. Now there's an arrow. It keeps going from that point on. But the function does not exist anywhere over here. Okay? So that's important. When we talk about domain, well, what's the starting point? What's the lowest point? What's the lowest value of x that can exist on this function? Well, it's right here, -5. Now, x can be any value higher than -5 because this arrow means that it keeps going off to the right. So x can be -5 and anything higher. It cannot be less than -5 because the function doesn't go beyond that point. So the way I write that, domain equals, okay, x is an element of the real numbers, but there's a restriction. X must be greater than or equal to -5. Now, if we think about the range, it's similar. Range is the y values. What's the lowest possible y value? -2. And what's the highest possible y value? Well, this graph, the function keeps increasing. So there's no maximum y value. It just keeps going on forever. So y must be greater than or equal to -2. All right, here's a crazy function. Starts here, ends here. There's no arrows on the ends of my graph, so that means the curve does not extend beyond these points. All right, so domain. The lowest possible x value is -5, according to this scale, and the highest possible x value is 4. So domain, x is an element of the real numbers, but it's in between -5 and 4. And the way I write that is -5 is less than or equal to x, which is less than or equal to 4. So hopefully you can see that in the notation, x is in between -5 and 4. Now the range is with the y values, so the lowest y value is -4. The highest y value is 7. So we're going to write the range in a similar way. Range equals, and then in my curly brackets, y is an element of the real numbers with the restriction that -4 is less than or equal to y, which is less than or equal to 7. So y is in between -4 and 7. And to finish things off, I've got an application problem here. So anytime you have a word problem, read through the question first and try to visualize the situation. A ball is kicked and its path can be modeled by the following function, where t is time in seconds and h is height in meters. Okay, so stop right there. We have an equation that represents the height of the ball in relation to its time after it was kicked. Picture a ball being kicked. It's on the ground. You kick it. What's going to happen to its height? Well, it's going to go up and then it's going to go down again. So as time progresses, we would expect the graph of the height to go up and then back down. So I would start by drawing a sketch of that. So here I just drew a little sketch of the graph of the height over time so that I can better visualize what's going on. All right, then I'm given the equation. So height as a function of time is equal to -5 multiplied by t minus 4 squared plus 80. So there's my equation. And the first question asks to explain the meaning of h bracket 5. H of 5. So remember, this is function notation. H of t is the height as a function of time. H of 5 would be height as a function of 5? Well, what's the 5 there for? What's the 5 replacing? It's replacing the t. So remember, in function notation, whatever's in the brackets is the value of your independent variable. So in this case, the 5 is the value of t. So the way I can answer this question, explain the meaning of h of 5, I can say that this is the height of the ball after 5 seconds. Okay, and my next question says, determine the initial height of the ball. This word initial means beginning or start. So determine the beginning height of the ball. Well, I drew a sketch. It looks like the beginning height is 0, but this is just a sketch that I made of what I think it looks like, but I'm given an equation, so I can actually figure this out mathematically. So determine the initial height of the ball. So I want to figure out the height when time is 0. That's the start, when time is 0. So really, I'm calculating h of 0. So that means in the equation, anywhere I see a t, I replace it with a 0. So then it looks like this. And now I just have to do the math to evaluate what this equals. So remember the correct order of operations, bed mass. do what's inside the brackets first. So 0 minus 4 is minus 4. After brackets comes exponents. I have an exponent right here. So whatever's in the brackets squared, that means whatever's in the brackets multiplied by itself. So minus 4 times minus 4 is positive 16. Okay, brackets, exponents, division and multiplication. Well, here's multiplication right here. Negative 5 times 16 is minus 80. And then we have our addition and subtraction. So minus 80 plus 80 is 0. So determine the initial height of the ball. The initial height is 0 meters. Now, still talking about the same situation. So I'm using this same equation as on the previous slide. Just put it up here to remind us what it is. So we're still talking about the ball getting kicked. It goes up in the air and then back down. How long did it take for the ball to land? Well, here's my sketch again. So I know the height starts at 0, it goes up, and it comes back down, lands on the ground again after a certain amount of time. But how long did it take for the ball to land? So basically I'm asking, how long did it take to get here? What's the value of t at this point? So anytime you have an equation and you're asked to solve for one variable, that means you need to plug in a value for the other one. So if I want to solve for t, that means I need to plug in a value for height. So what's the height when it lands on the ground? 0. So I'll replace the height with 0. And then I can solve for t. So I'm doing some algebra here. I have to isolate for t. That means I need to do the opposite operation to start moving all the terms that are not t to the other side. So I'll start by subtracting 80 from both sides. Now I have to divide both sides by minus 5. So I have 16 equals t minus 4 squared. Now what do I do with the square? Well, what's the opposite operation? Square root. So I have to take the square root of both sides. So now I end up with 4 equals t minus 4. So to get t by itself, I have to add 4 to both sides. So I end up with 8 equals t. So it took 8 seconds for the ball to land. Last question, determine the domain and range for this scenario. Okay, if you took this equation and put it into a graphing calculator, it would make a graph that looks like this, except the parabola, the curve, would continue on down and down into the negative values for y. But the question says determine the domain and range for this scenario. Well, the scenario is the ball being kicked. So it doesn't make sense for this curve to go into negative height values. That would mean the ball is underneath the surface of the earth, right? So the ball's not doing that. You're not kicking it. It goes up and then down through the earth, out the other side and into outer space. It's not doing that. It's stopping here. So we have to put realistic limits on our domain and range for a realistic scenario. So my domain, well, t, the time, is any real number between 0 and 8 seconds. For my range, I'm looking at height. Height is an element of the real numbers, but it's between 0 and 80 meters. So just the way I got the 80, you might not remember this from grade 11, or even grade 10, but when you look at an equation for a parabola, this is in vertex form, so the coordinates of my vertex are 4, 80, so after 4 seconds, the maximum height is 80 meters. I just remembered that. You could also figure this out, knowing that the maximum point's going to occur halfway between your two x-intercepts here, so you can plug in a value of 4 for t into the equation. 4 minus 4 is 0, 0 squared is 0, times minus 5 is 0, plus 80, your answer is 80, so your maximum height's 80. All right, all that to say, your range is, well, h is between 0 and 80. Okay, so there you have it. We looked at function notation, we looked at domain and range, and then we applied all of that and did some math along the way And there you go. Now it's time to practice.